if there are no other questions, oopsie, where's everything now? If there's no other questions, let's move on. All right, so I told you I would get into this third topic in this chapter, so we still got one more topic before we're done with this unit. And at the end of the unit, I will be doing it's not a test. I'm not going to call it a test. I'm going to call it an assessment because it's really, I'm not going to make it worth that many points. But you will have to answer some questions. But the way I do it is all the questions are questions that you've basically seen before. So, and it's open book, open notes, open everything. You just have a time constraint. But don't worry about that right now because we still got to go through all this relative motion stuff. And I can't imagine us getting to the assessment before next week. And so most likely I will start talking more about the assessment next time we meet tomorrow. Because I haven't even got it ready yet. I haven't even made it. So just put that on your radar screen, okay? All right, so relative motion. I don't even have any notes for you on this because it's really nothing new. It's just looking at things from, maybe I should put a few little notes on it, but I think it's pretty straightforward. Okay, here's a problem of boats traveling upstream with respect to the water of the river. The water itself is flowing with respect to the ground. So a boat's moving on something that's moving with respect to the ground. So this is what's referred to as relative motion, where you have an object that's moving. Up until now, every time we've kept track of the motion of an object, it's always been with respect to a coordinate system that is in projectile motion was always attached to the ground some way. It was either attached to the top of a cliff or the top of a building or the bottom of a cliff or the bottom of a building or some sort of fixed point, right? And we'd say, okay, so all of the motion of that one, there's one problem where we did two objects, but they're both, all the motion was referenced to a fixed reference frame, like an x-axis, where the motion of both objects was measured relative to one reference frame. All right. So the question becomes, well, what happens if you can't do that? What happens if you have motion of one object, but you can only measure it relative to another object that itself is moving? So one thing's moving with respect to another thing that's moving, and that thing could be moving with respect to the ground. How do you deal with that situation? And conceptually, I don't think it's that difficult. The one example problem I always end up talking about is, let's say, and I think this is the easiest one to understand, is if you're in a bus. Let's say you're in a bus driving down the street, okay? And you're in this bus driving down the street, and you're sitting in the back of the bus, just sitting in a seat, right? So your velocity with respect to the street is the same as the bus's velocity with respect to the street, as long as you don't get up and start moving, right? So let's say the bus is moving 10 meters per second with respect to the street. So both you and the bus are moving at 10 meters per second with respect to the street. Does that kind of make sense? But what happens if you were to get up? I know you're not supposed to do this, but if you were to get up and start walking forward in the bus, okay, is your velocity now the same as the bus's if you're moving with respect to the bus? And when I talk about your velocity, I mean your velocity relative to the street. No, it's not this, right? So now you're moving with respect to the bus, and so now that makes your velocity, your velocity relative to the street and the bus's velocity relative to the street different. Okay, but how do you figure it out? Well, let's say you're to put a whole bunch of meter sticks along the floor of the bus, and you were to watch how many meter sticks you walked forward along during, say, a second of time. And let's say you were to walk exactly 2 meter sticks forward. Those meter sticks are on the floor of the bus, so the meter sticks are moving with the bus. So question becomes, if you move 2 meters per second forward with respect to the floor of the bus, while the bus is moving 10 meters per second forward with respect to the street, how fast are you moving with respect to the street? Just count up the number of meters. The bus moves, yeah, exactly. The bus moves forward 10 meters, but in that same 1 second that the bus has moved forward 10 meters, you move forward an additional 2 meters. So you've actually gone 12 meters in that 1 second. So your velocity must have been the 10 plus the 2. Okay? That makes sense to everybody? Okay, so what happens now if you get to the front of the bus and you start moving backwards at 2 meters per second? So the bus goes forward 10 meters, but you've gone backwards 2 meters. So how many meters have you gone in a second? Right, 8 meters in a second. Does that make sense? So that's how relative motion works. It's your motion, your speed relative to the bus, plus the bus's speed relative to the ground gives you your speed relative to the ground. And all of these relative motion problems work out the same way, even in 2 dimensions. Because remember, velocity in 2 dimensions is going to be a vector, right? But you just, so how do you handle it? Well, you just do the same addition or subtraction, but you do it with vector addition. And it works out the same way. So it's the velocity of something relative to something that's moving plus the velocity of that something relative to the ground gives you the velocity of the original object relative to the ground. Okay? And I think as you see a bunch of example problems, you'll see how this works. So here's this first problem, and this is going in one direction, right? The boat and the river are moving in the same one dimension. One's moving in one direction, one's moving in the opposite direction, but it's still a one-dimensional problem. All right, so the boat is moving upstream at 14 kilometers per hour. The water is moving downstream at 9 kilometers per hour. What is the velocity of the boat with respect to the ground? What do you think? What's the difference between it's like you take the bus's velocity. Let's call it, yeah. You have to call it. You have to say one. Let's say going downstream, the direction of the boat is the positive direction. So it's the boat's velocity relative to the water, 14, plus the velocity of the water relative to the ground, which is a -9, would give you a +5, right? So it's the boat's velocity relative to the water plus the velocity of the water relative to the ground gives you the boat's velocity relative to the ground, okay? Does that make sense? Okay, so now you take it a step further. Now you have a child that's walking on the boat. So now the child is walking with respect to the boat, which itself is moving with respect to the water, which itself is moving with respect to the ground. So now how do you do? You just add the velocities in with plus or minus signs depending upon which direction they're going in, right? So what do you think? The boat's moving from front to rear. So that's in this direction, right? That makes sense? So I think I didn't quite put it in the order in which you would normally do it. It'd be -6 plus 14 minus 9, you know, starting from the original person that's moving. But yeah, you have the boat's moving forward 14, both the river's moving backwards 9, and the child is walking backwards 6. So 14 minus 9 minus 6. So actually the child is moving with a relative motion to the ground of -1. Does that make sense to everybody? Right? So in other words, if you had to draw another arrow on the paper there, I should have probably put a comma there, meaning that the answer is -1 kilometer per hour, right? But that means that it's going downstream. Yeah, it's not. It kind of looks like a double negative, doesn't it? The way I wrote that. Yeah, it's not supposed to be a double negative. That makes sense to everybody? Okay. All right. Yeah, right. That would be not using the double negative. But I put that -1 there. It's the minus sign that tells it's supposed to tell you that it's going. See, this was a +5. that means it's going upstream. This is a negative, so that means it's going downstream. All right. How much time do we have? Can I get this done in 5 minutes? Because I only want to keep you 30 minutes on a 40-minute day. All right, so let's see if we can get this one done. Okay, so another one-dimensional problem. This one's a little bit more complicated. Have you ever been to one of these airports that has these like moving walkways? Where have I been that I've seen? I think Salt Lake City? Denver? I think maybe Denver has one too. Denver's a big airport. I can't remember which airports. Anyways, you're at an airport. I don't know if you've seen these moving walkways. It's like a conveyor belt, but it's for people, right? And you can either stand on it or walk on it, right? And it's because they have these long corridors that are, people have heavy luggage, and so they put in these moving walkways. Okay. Fuzzy there. Okay, so you got to read this carefully. So you got a guy named Peter does not use the moving walkway. So, and he takes 150 seconds to walk the same corridor. You've got a guy named Paul who stands on the moving walkway, and he moves that same distance in 70 seconds. And then you have Mary, who walks on the moving walkway. So when Mary's on the walkway, she has a velocity relative to the walkway, the moving walkway, and the walkway has a velocity relative to the ground. So she's going to have a velocity relative to a ground, which will be the sum of her velocity relative to the walkway plus the walkway's velocity relative to the ground. And that would give you her velocity relative to the ground. Does that make sense? It's the same thing as walking on a bus. Okay, but they're asking how long does Mary take to move through the corridor? Okay, assuming that Peter and Mary walk at the same speed. Okay. All right, so that's a little bit more complicated this way. So how do you do this problem? Well, notice they didn't give us the distance. Okay, if we had the distance, we could divide by those times and get the velocities. So a couple of ways you could do this. I don't know if this is really obvious, but the fact that they didn't give you a distance should kind of tell you it doesn't matter what the distance is. You're going to get the same. It's all proportional because the speeds are constant. So it doesn't matter what the distance is. So if you wanted to, you could probably just pick a number for the distance, but I'm not going to do that. What I'm going to do is I'm going to just say x. And what's going to happen is when you set up the problem, x is going to cancel out of the equation, and so the x is not going to matter. So I'm going to say the velocity of Peter, who just walks without using the corridor, is x over 50, x being the length of the corridor. Okay, and the velocity of Paul, standing on the belt, the conveyor belt, right? So this velocity of Paul is basically going to be the velocity of the walkway relative to the ground, because he's standing still on the walkway. Does that make sense to everybody? Okay, that's going to be x divided by 70. Okay, so it's the velocity of Mary relative to the walkway plus the velocity of the walkway relative to the ground, and that's v Paul, equals velocity of Mary relative to the ground. Okay, and so if you if that makes sense, right? So okay, now this kind of I put this I move the velocities around. So I don't know. I hope this makes sense. Sorry. Did that make sense, what I wrote down? I don't know if I'm not explaining this really well. Okay, so okay, so hopefully this makes sense to you guys. So if you take the distance, so I'm gonna write down velocity for Mary as being x over the time that Mary takes to go, because we don't know that. All right. So velocity of Mary is just, I calculate the same way as I got the velocity of Peter and the velocity of Paul. Okay. That kind of makes sense. All right. So if you put that in, right, put in the two velocities for Peter and Paul, then you can see immediately what happens. Exactly what happened is exactly what I said happened. Notice that you get an x in all three terms, so the x is going to cancel out. So the x is going to cancel out, and I did a little bit of math here in my head, right? You're going to have 1 over t Mary plus equals 1 over 150 plus 1 over 70. And so you solve for, take the inverse of both sides, right? And so the time of Mary should be 1 over 150 plus 1 over 170, and it ends up being 48 seconds. Okay. All right. Okay. All right. So any questions on that or on the lab or anything like that? Because it is now 9 o'clock. You got 11 minutes before your next period, and there's no way I can. Oh yeah, I read those when I was a kid. Only got to the second book. Never got to the third book. You should read the book. The movies. They always had trouble. They've made what? How many different versions? I've seen 2 different versions of the book made into a movie. They all get terrible reviews, and that's because the story is so complicated. It's really hard to make into a movie, and you always lose a lot in translation. So read the book. A lot better than the movies. All right. So I'm going to let you go at this point, unless there's any questions. We'll see you back here tomorrow. Okay. See you guys. Take care. Have a great day, guys.